So welcome back, everyone. Last lecture, we talked about two-player zero-sum games. And so we're going to review that a little bit. And this time, we're going to start bringing together reinforcement learning and games. And then we're going to actually play a few games in this class. So hopefully that'll be fun. OK, so just as a review, last time we talked about the minimax principle. And this is the way that we solve games. So remember, in a game, you have different players being in control at different states, which means that you can't just max over everything or take expectations. You actually have to max and min. So this was a game tree that we looked at last time, where at the root node, the agent is trying to maximize its utility. And at the next level, the opponent is trying to minimize the utility. So at these min nodes, you take the minimum over the outcomes of each of these subtrees. And then at the max node, you take the max. So the minimax value of this game is 1, which corresponds to the agent choosing the action B here, and then the agent choosing action 1. Okay. So we talked about ways of speeding up minimax search. If you want to keep it exact, you can use alpha-beta pruning. In alpha-beta pruning, remember, you keep track of lower and upper bounds on the possible values of each of the states in your ancestral tree. And for example, here, after you've explored this part of the tree, you know that this is at least 1. And you come over here, this is at most -5. These don't overlap, so then you don't even need to look at the 15. Okay? So we also looked at evaluation functions. And this is if you want to bring in domain knowledge and you don't mind being approximate. So then you can just define an evaluation function to assess whether a state of the game is good for the agent or not. So we looked at this one in chess, which combines a variety of different factors related to how many pieces you have and how much mobility and control of the center you have and so forth. So this was very much about manual heuristics. So now the question I want to pose is, can we learn the evaluation function? Because if we can learn it, then maybe we can do better than a hand-coded system. So indeed, that's what we're going to do today. We're going to use reinforcement learning, in particular TD learning, to learn the evaluation function. So you have to bring back your memories of reinforcement learning, and let's dive in. So just as a refresher in reinforcement learning, there are two quantities of interest. So this is value-based reinforcement learning. So you have V pi of S, which is the value or the expected utility that you would obtain if you followed policy pi from state S. So in a state S, you follow some fixed policy, and this is how much value you would pick up. And there's also Q values, which are have an extra argument, which takes the action here. And this is the value of utility when you first take action A when you're in state S, and then you continue to follow policy pi. Okay, so these are the two quantities that show up over and over again. We saw them first for policy evaluation in MDPs, and then we saw them in SARSA, and now they're going to come back again. So remember the SARSA algorithm from reinforcement learning. So this was an on-policy algorithm, which means that it's estimating the Q values of the current policy that you're following, as opposed to the optimal policy, which might be not the one you're following. And SARSA was also, the main insight was bootstrapping, remember, where you're updating the Q values towards a target, and the target, rather being just empirical utility of the full rollout, is an immediate reward plus an estimated future reward. Okay, so here's the SARSA algorithm. As you run the reinforcement learning algorithm, every time you see a state and you took an action and you got a reward, and then you ended up in state S prime, and then you took another action, then you perform the following update. First, you look at the reward, that immediate reward that you just got, and then you form an estimate of how much reward you would get after that. So after this reward, you ended up in state S prime, and now you're taking action A prime. So that estimate sort of packages up your belief of how much reward you're going to get. Okay, and then what you're going to do is you're going to nudge Q pi of SA, which is your current Q value estimate, in this direction by some learning rate eta. Okay, and you keep on doing this over and over again. All right, so in code, it looks something like this. So I instantiate an RL algorithm SARSA. And then remember the RL algorithm, it implements two functions, get action. So I'm in state 1, and I get an action, and then the environment does something with that action. And then I incorporate feedback, which tells the agent what happened. So incorporate feedback state 1, I walked, I got a reward of -1, and I end up in state 2, and I haven't finished, and so on and so forth. So get action, incorporate feedback, get action, incorporate feedback. Okay, so one thing that's interesting I want to emphasize is that the strong connection between Q values and policies. So SARSA computes Q pi, which is the Q value of the particular policy pi. But given this Q value, I can read out a policy. And the policy I read out is simply, well, I just take the best action here, so argmax of A over Q pi of SA, and that gives me a particular action to follow. So you can think about this as one step of policy improvement, where here is the value of this particular policy, and a new policy is simply, well, I'm just going to myopically optimize over the next action, and then I think about following the best whatever values I get after that. Okay? So the whole point of this is that given a Q value, you can read out a policy just by argmaxing it over A. Okay. So now I'm going to invoke another thing. We looked at policy evaluation from MDP. So remember, in MDPs, you get the transition and the rewards, and you know how the world works. In reinforcement learning, you don't. So in MDPs, we have these set of equations. So we define a value of a policy to be simply the Q value of the S and the action given by that policy. And then separately, you can also define a recurrence for Q pi of SA, and that just corresponds to summing over all possible successor states when you take action A, weighting by the probability of that transition, and then immediate reward plus an estimate of the future. So just as a recap, SARSA is a reinforcement learning algorithm. It computes Q values, Q, which is a function of SA. I can get a policy out very easily. Now the question is, let's say I just gave you V pi, could you compute a policy from that directly? Can you read out the policy? If I only told you essentially how good various states are, can I get a policy out? Well, I guess the question is like, what do you need to get a policy out, right? And in some sense, well, you look at this and you say, well, if I'm given V pi S, I can just compute Q pi SA using this formula, and then I take the argmax over A, and then that's my policy, right? So I'm only given V, so I don't have Q, but the Q is in some sense a one-step transition from V. But here's the catch, is that computing this requires knowledge of the MDP. So this is why, in general, you can't just estimate a value of states, right? Because if I don't know how the world works, you can tell me this state is great, this state is bad, this state is great, but that doesn't tell me what actions, how does that connect with actions? And the thing that connects actions and states are things like the transitions, but I assume I don't know the transition, so that doesn't help me act. Whereas if I have a Q value, this sort of binds the action into the value. So I know that in the state, not only is it good, but I take a particular action, and that gives me some value. Okay. So that's why when we started with reinforcement learning and its full generality, we only looked at SARSA and Q learning because we need policies. Now, however, for games, we actually do know the transition and rewards, unless you're in a cruel game where you don't know the rules. Most of the time you're playing a game, you know perfectly the rules. Things might be even deterministic as we've defined it. For example, chess, Go, everything's deterministic, everything's fully observed. So there's no uncertainty. So then, given a V value, it's actually pretty trivial to compute the best policy. You simply look at the action. You're in a state S. You look at the action. You basically consider all actions. You see where they go. So remember, there's a deterministic successor function that takes a state and action and tells you what successor state you end up. And you just evaluate how good the resulting state is. Okay? Well, wait a minute. But if we already know the MDP, then why are we using reinforcement learning? Right? I thought the whole point of reinforcement learning is that you don't know the MDP. If you know the MDP, just do value iteration. So in principle, you could also do value iteration for games because there's in some sense, no need to learn anything. You already have everything in front of you. But the problem is usually for games, besides, tic-tac-toe or something, the number of states is just vast. It's going to be exponential, and you won't be able to do value iteration, which grows with the number of states. Okay, so therefore, we're going to use reinforcement learning. And it's important to know why we're using reinforcement learning. It's not because we don't know the MDP. We actually know the MDP quite well. But it's because the number of states is exponential, and reinforcement learning allows you to use function approximation and effectively reduce the number of states. Okay, let me pause there. We did a bit of review of Q values, V values, policy evaluation, and SARSA, and some motivation for MDPs and reinforcement learning. How does the first policy update simplify to this one? Is that the question? Yeah, so in a game, the transition probability is 1 for one particular S prime. And that particular S prime is suc SA. That's a function. Okay, so the summation goes away. And then in a game, all the reward is at the end. So this is 0 for essentially all transitions. And then discount is 1. So then you end up with just V pi. Yeah. Okay, so now let's actually talk about turning this into an algorithm. So TD learning, the way to think about it, if you had to just kind of remember one thing, is TD learning is as to V pi as SARSA is to Q pi. Okay, so SARSA estimates Q pi, TD learning estimates V pi, and basically that's the only difference. Okay, so in SARSA, Q pi tells you how good each action is from a given state. And in TD learning, all V pi is going to tell you is how good each state is. And since we know the action to next state mapping, that's all we need, because we just need to know how good states are. So this is good, and it simplifies things because we have a function of just the state rather than the state and the action. So it's a minor point, but it does make some things easier. Okay, so now we're going to assume we do function approximation. So remember, in function approximation in reinforcement learning, we take, instead of keeping a tabular representation, meaning for every state we have a separate value that has nothing to do with any other value, we're going to define a function, a parameterized function, also written v, which takes as input s, and then depends on some weights w. So these are the parameters of that function. As you vary w, you get different functions. So in deep reinforcement learning, typically v pi of s is called a value network. Okay, so here's the nutshell, TD learning in a nutshell. So you get a piece of experience. So you are in state S, you took action A, you got reward R, and then you ended up in state S prime. So the model predicts that this state has this particular value, Vs given some parameters. Okay, so based on this new piece of information, how can we compute a refined estimate of that value? So we define the target, which incorporates this piece of experience by this bootstrapping, where you have the immediate reward plus some discount gamma times the value of the successor state, given the same set of weights. Okay. So this is very similar Q learning. It's just you have V's instead of Q's. And now I don't need an A prime because this is just a value function, not a Q function. So now, to move the model's prediction towards the target, I'm going to define a loss function. And the loss function, I'm just going to use the square loss here to be the square difference between the model's prediction and the target. And then getting that loss function, I can just take a gradient step by moving the weights in the opposite of the gradient of this loss function. Okay? So to put that in more, summarize that in an equation. So on each piece of experience, I'm going to look at the model prediction, look at the target, and I guess so if you differentiate this, you'll find that there is this sort of natural form where you have the difference times the gradient of what's inside, which is just the gradient of the value function at w. Okay, so one important point is that this term also depends on w, but I'm going to treat it as a constant. So remember in the second lecture or so, I had this, we were doing computation graphs and you could detach. So this is where you would detach this, because this is, when I backprop through this, I only want to backprop through this first w. Yeah, so let me explain that again. So you can think about the target as just a value, a constant, okay? And then all you're doing is you're saying your model prediction, move it towards the target. The target is fixed, you don't change it. And that corresponds to this gradient. But however, the target also depends on w, implicitly, or actually explicitly. But for the purposes of computing a gradient, I'm not going to differentiate through that. Okay, so let's see a code implementation. So we're going to do TD learning for this tram problem. So I'm going to define the MDP, exploration policy, which either walks or takes the tram. And then TD learning, I'm going to pass in the MDP now. So if I just want to evaluate a value of a policy, I don't need this, but I need the MDP to be able to compute the policy, as I argued earlier. So this is for a general MDP, not just games. So in the R algorithm implements two things, as usual: get action and incorporate feedback. So when I get the action, TD learning, if I'm doing epsilon greedy exploration, I either with probability epsilon explore, or with probability 1 minus epsilon return pi. And what is pi? Pi corresponds to the policy that given by v pi, which are the values I'm estimating. So what I'm going to do is I'm going to compute the q values, because I only have v. So I compute the q values for every action. So for every action, I'm going to sum over all the possible successors of that action, weighting by the probability of that transition times the immediate reward plus the discounted future reward. So this is where v comes in. So if I take v, I combine it with my knowledge of how the world works, the transitions, and then I'm going to get a q value as a result. And then that is going to give me a set of q values. And then I'm just going to take the action with the highest q value. Okay, and in this case, this is walk. So given these v values, I can compute a policy. Okay, that's going to allow me to act. And now when I act and the environment sends me feedback, this is what I'm going to do. I'm going to look at the predicted value of a given state. I'm going to look at the target, which is reward plus discounted of the next state. And then I'm going to just perform this update. So notice I'm not doing any function approximation here for simplicity. If there were a function approximation, I would form a loss function and take the gradient, but I'm just keeping it simple for now. And in the tabular setting, this has a simple interpretation, which is I'm just moving it towards the target away from predicted at some learning rate. Okay. And as in this example, I predicted 0, the target was -1, so I'm going to nudge the value of state 1 to be minus 0.1, which is in this direction. Okay, so then I do this over and over again, and that is essentially TD learning. Okay, to summarize, TD learning estimates v pi from experience. Okay, so remember v pi is the value of a particular state under some policy pi. So this tells me basically if I'm following a policy, how good are various states. And it is on policy. Notice that we're only rolling out with the policy pi and we're not considering any other actions. Whenever you see a max over actions, that usually means something like off policy or Q learning. If you don't see that, it's probably on policy. That's a good rule of thumb. And then we're using bootstrapping, where we're looking at the target consists of the model. That's a sign that it's bootstrapping. Now let's specialize TD learning for games. What we did is TD learning in general for any MDP. Now we're going to adapt it to games. So what's special about a game? Well, as we discussed earlier, transitions are deterministic, at least in the games that we've looked at so far. So when you make a move, it does one particular thing. And there's no utility until the end of the game, and then there's two players, agent and opponent. Okay, so in some sense, maybe I lied a little bit. It's not necessarily a special case, but it is The fact that you have deterministic transition, that's a special case. No utility at the end, that's a special case. But this idea of two players, the agent and opponent, remember that is the thing that's actually special about games. So how do you deal with that? And the way you deal with that in the context of adapting reinforcement learning is actually quite simple and elegant. You just let the agent and opponent use the same value function. So this is known as self-play, where you're essentially saying, agent and opponent, your minds are, I guess, wired in some sense, and you're just going to use the value that I'm going to estimate to drive your decisions. But of course, the agent and opponent are not doing the same thing. The agent is trying to maximize, and the opponent is trying to minimize. Which means that there's a small tweak that we need to do. So this we saw earlier, that given an estimate of v pi, we can read out a policy for the agent by just choosing the action that leads to the best state under v pi. But what is the opponent trying to do? It's trying to do the opposite, right? It's trying to minimize. So you just replace the argmax with argmin, and you say that's the opponent policy. Okay? So it's actually pretty nice that all you are focusing on in TD learning is estimating these v pi. And once you have v pi, you can play either the agent or the opponent. And this is generally true. If you know what's good and what's bad, you can choose to do the good thing or you can do the bad thing. So let me instantiate this just as a fun example for the game of backgammon. So here's the way backgammon works. So you have this board. It consists of these triangles called points. There's two players. In this picture, there's the red player and the white player. Each player has a set of pieces. And the goal is to move your pieces off the board. Okay, so if I'm the red player, I have my pieces here. I'm trying to basically move all these pieces around clockwise to my home board and then off. And the white is going to take all these pieces and try to move it counterclockwise and off the board. Okay, so how do I move pieces? There is dice involved. So I roll two die, and let's say it's white's turn. Okay, I roll two die, and the die determine the number of spaces I can move. So if I roll a 3 and a 5, I could say take this piece, and I can move it 3, and then another 5. Or I could take, let's say, this piece, I move it 5, and take this piece and move it 3. Okay? So what makes this game interesting is that if you land on a point with one opponent piece, I guess there's no examples here, then you move that piece to the bar. You sort of crush the piece and that goes to the bar and it sort of has to start over. So that's bad for your opponent, good for you. But if you have, but you can't land on a point with more than one opponent pieces. So generally the strategy is that you're trying to put your pieces in tall stacks so that they're safe from your opponents. But at the same time, you have to move everyone across. So this is probably a better move because this allows you to have two, so you don't have any exposed singletons, essentially. Okay, so I think I'm not sure if there might be another rule, but that's basically the gist. So notice that this game has randomness in it. So it's a little bit different than MDP or a classic game. But remember, we shouldn't be afraid when there's some sort of slight variations because as long as we understand the principles, we can write down these recurrences and then everything kind of makes sense. So the first thing is to think about the dynamics of the game here. So we're going to use pi dice to denote the dice as I guess, a player in some sense, which is a fixed policy and just generates the values of the two die. Okay, so the die pi dice is going to move first, and then it's going to be the agent's turn. And then when the opponent rolls, that's going to be another pi dice, and the opponent's going to move. And then agent's going to roll, and then agent moves, and so on. Okay, and the reason that the dice has to be before the pi agent is because the agent's move depends on what the outcomes of the dice were. Okay, so when we do TD learning for backgammon, we are trying to learn pi agent and pi op at the same time. Remember, this is self-play, but pi dice is fixed. If you were in a cruel world, then you could also play against adversarial dice, but I imagine that would be a much harder game to win. So one example of how you could proceed then is if you want to apply TD learning, you have to define how the value function is parameterized. Okay? So typically you have a game, it has a game state, and you have to turn it into a vector for machine learning to work. So here is an example of how you define a vector for each state. So we did this in the machine learning section of the class. So you have a state, let's say the simplified state. Typically you can define a set of features that capture the state. So for example, a feature might be the number of O's in column 0. Is that number equal to 1? That's true, so that's a 1. Number of the O's on the bar, that's a 1. The fraction of O's that are removed, so 2 out of 4, that's a half. Number of X's in column 1 equals 1. Number of X's in column 3 equals 3, that's a 1. And it's an O's turn, and it's 1 here. Okay, so every state of the board gets mapped into a feature vector. Okay, so now if you have a feature vector, you can do many things. You can define a linear value function, which we talked about. So this is basically linear regression here. Or you can do something fancier. You can define a multi-layer perceptron and have multiple layers. You can do a number of things. Okay, and then you just apply TD learning. So next, I'm just going to go through. This part isn't technical, but I think it's interesting to reflect on some historical examples where machine learning and reinforcement learning have been useful in game playing. So I think I have mentioned this on the first day of lecture. Checkers was a very early example of where learning was helpful. So Arthur Samuel in 1959 trained a chess program, and it learned by playing itself repeatedly. So this is perhaps one of the earliest examples of self-play in action. At that time, compute was limited, so you couldn't really do that much, deep learning. So you had to invest time in getting features. So the type of, I gave you a very simple set of features for backgammon, but you can define much more complicated features. They use a linear evaluation function, linear value function, and then also define some intermediate rewards. Remember, in games, the true reward is only if you win or lose. But that is a very hard thing to learn from because it's a delayed reward problem. So they essentially added some intermediate rewards to make the problem easier. They also did alpha-beta pruning with some additional heuristics which are domain-specific, alpha-beta pruning we talked about. And this reached an amateur level of play. So it could probably beat me, probably. And this, you got to remember 1959. So this was on 9 kilobytes of memory. So pretty good. Okay, so backgammon, which we just talked about. So the big result in backgammon was this program called TD Gammon made by Gerald Tesoro in '92. And this was an agent that also learned by self-play, except for it was 1992 instead of 1959, so they could do it 1,000,000 times. And because the compute was more plentiful and you can get more data, they actually used fairly simple features, and they used a neural network and had no intermediate rewards. Okay? So you could see the kind of the direction. As you get more data, more compute, you don't have to engineer features quite as much. And now this reached a human expert level of play, not just an amateur level. And one of the earliest examples of providing new insights into the game. So it provided new insights into how the first move should play out. Okay, and then there's Go, which I think is more of in recent memory. So in 2016, there was AlphaGo. I want to highlight AlphaGo 0 because it's much more bullish on reinforcement learning. This learned by self-play as well. So they played about 5 million games. Here at this point, it was also dumb features, and you just had the stone positions. Right? So in Go, there's a lot of complexity about, what pieces are live and how everything's connected and how many degrees of freedom there is. And previous programs, you would try to encode all of that knowledge into features. But here, we're just saying, machine learning algorithm, these are where the pieces are, go figure it out. And this was obviously using a deep neural network, no intermediate rewards. They did have to use Monte Carlo, tree search, which I'm not going to talk about, but it's a search algorithm that allows you to essentially get a better policy rather than just taking the action that gives you the next reward. So you can think about this as a less greedy version of the types of policies that we've been looking at. So this actually beat AlphaGo, the version from 2016, which beat Lesido in 2016. So, of course, at this point, Go playing systems are much better than humans. And similarly, this also provided new insights into the game. Okay, so these are 3 examples of just ground out how these techniques that we've been seeing in the class map onto real world examples of gameplay. Okay, so that's all I'm going to talk about in terms of TD learning. Okay, so next we're going to look at 2 generalizations or extensions, if you will, of the types of games that we've been looking at. So we've been looking at turn-based games, we're going to look at simultaneous games, and we're going to also go beyond the zero-sum assumption. Okay. So far, we've been talking about turn-based games, and now we're going to talk about something called simultaneous games. And simultaneous games, a famous example is rock, paper, scissors. 2 players have to play at the same time. And so here's a question for you to think about. Can you still play optimally if you reveal your strategy to the other player? Okay? So obviously, if I am playing rock, paper, scissors and I say, I'm going to play rock, that is not very smart. Okay? But is there a way to play optimally if you still reveal your strategy? And the answer turns out to be what kind of strategies you're allowed to do. So in turn-based games, we have that nailed, right? We just compute the minimax policies using a game tree. And so the game tree naturally models the turn taking, where each node, only one player is moving. Okay? But in simultaneous games, 2 players have to move at the same time. So we can't use a game tree anymore. Right? You can't have this. If 2 players are trying to move here, then it's confusing. Are you maxing or are you mining? And that doesn't work. Okay, so we're going to focus first on zero-sum games, zero-sum simultaneous games, and then we're going to do the non-zero setting. Okay, so we're going to start with a few definitions, and then there's a theorem that essentially solves it. Okay, so I'm going to present to you another game which is hopefully more obscure than rock, paper, scissors. Okay, so here's how the game works. So you have two players, A and B, and each is going to show either one or two fingers. If both show one, then B gives A $2. If both show two, then B gives A $4, and otherwise, A gives B $3. Okay? So intuitively, A wants both people to play the same number of fingers, because that's where A can win. And there's A really wants it to be more two than one, right? But if A always plays two, then B is going to play one, and then A is going to lose money. Okay, so there's sort of this balancing act here. Okay, so while I'm going through this, maybe in the back of your mind, you could just think, what's the strategy here? All right, so let me introduce some formal notation. So this is called a single move simultaneous game. Okay, so it involves just playing the game, single move, you're done. There's no state. There's two players, A and B. We're going to define this payoff matrix, which is essentially going to be the equivalent of the value function or the reward function. And it takes two arguments, A and B. And for each action pair, I'm going to give you a value. And that value is A's utility. And because it's zero sum, B's utility is just the minus of that. And again, there's no state, there's only one action. Okay, so this is what it looks like for two-finger Mora. Let me just write this on the board, so this is as a handy reference. So I have, so A can play either one finger or two fingers, B can play one finger or two fingers, and then if they both play one, then A gets two. If they both play two, A gets four, otherwise A might loses three. Okay, so that's the payoff matrix. Okay. So just to ground things out a bit, so there's two actions, 1 and 2, and this is the payoff matrix. So V of 1 and 1 gives you 2, and so on and so forth. Okay, so that's a game. Now, what is the equivalent of a policy here in game theory? It's known as a strategy. And there's a pure strategy is a deterministic policy. And a deterministic policy just is a single action. And a mixed strategy, also known as a stochastic policy, is a distribution over actions. So for example, in two-finger Mora, always 1 is a strategy. And this means for the action 1 finger, I'm going to have probability 1. Okay, another way I'm going to write that in math is pi, the policy is a vector of probabilities of each action. So for 1, I have probability 1. For 2, I have probability 0. And for always 2, that is the strategy where all my probability mass is on 2 fingers. So written in math, it's pi equals 0, 1. And if I were playing uniformly at random, then I put 50-50 probability on each action. Okay, so I've defined the payoff matrix, the policies, and now I can define the value of the game, which combines them. And in math, the value of the game, according to two mixed strategies, pi A and pi B, is I'm going to consider every pair of actions, A and B, the probability of A playing this action and B playing this action, notice that they're independent, and times the payoff matrix value of action A and B. Okay? So in code, if I have this payoff matrix, V, that I'm going to pass in with, let's say, the uniform policy for both players, this is what I'm going to get. So I have this payoff matrix, I have two policies, and then, this is pretty straightforward. For every possible action with A with probability A, for every action B with probability B, I'm just going to sum up the values. Probability A times probability B times the corresponding entry in the payoff matrix. Okay, so if I do that, then I get a value of 0. Okay? And this sort of makes sense. If I take the average over all these 4 values, I should get 0. Okay, so everyone's playing uniformly. The value of this is 0. Okay, so now, what happens if player A plays always 1 and player B plays uniformly? Okay, so the value is going to be minus 0.5. So you can think about this, in this case, player B is uniform between these two, and player A only plays 1, so that means it's going to be average of these two values, and that's going to be minus 0.5. Always 2 means I'm always 2 down here, but uniform over these, 1 and 2, and that's going to give me the average of minus 3 and 4, which is 0.5. And then you can look at if A is playing uniformly and B is playing 1, then it's going to be the average of these two, and that's going to be minus 0.5. And the fourth case is uniform. A is playing uniform over 1 and 2, and B is playing only 2, and that's going to be the average of these two, and that's going to be 0.5. Okay? So hopefully game evaluation is clear, and just to build some intuition, it makes sense that, for example, player 1 wants to play 2 more, and if B is playing uniform, which is a sort of generic strategy, you can kind of get away with playing 2 and getting some value. Okay, so in some sense, it's much simpler than having states and actions and transitions and rewards and discount factors. But the solution is actually kind of more subtle here because of the simultaneous nature. All right. So how do you come up with the optimal strategy here? So just to have a bit of fun, I want everyone to find a partner and try playing like a few rounds and see if you get any insights. All right. So how did people do? Anyone figure out a good strategy that worked for them? It shouldn't be that. This is fairly subtle, so I'd be very impressed if you guys came up with the optimal strategy. And one other caveat is that this is meant to be a single move game, right? So you play once and you're done, right? What's happening, obviously, when you play an iterated game, now there's state, because now you have the history of what the other person's doing, and that changes the dynamic. So it's not quite the same game anymore, but anyway. Okay, so let's try to solve the game. Okay, so probably you're thinking, now you're dying to know, like, what's the optimal strategy? So the game, remember the game value. It's very simply defined as V of pi A and pi B. So, but the problem is that player A wants to maximize this quantity and player B wants to minimize, and they want to do it at the same time. So you get into this sort of jam where, like, how do you move forward? Okay? So how do you break out of jam? Well, you just have to let someone go first. Okay, so we're going to see what we can do here. Let's let someone go first. So first, let's consider pure strategies. So when players are just playing a pure strategy, what happens? Because this case we know how to do, right? This is just normal minimax. So let's say player A goes first. Okay, so player A is trying to maximize, player B is trying to minimize. So if player A goes first, then whatever happens, player B can just play the opposite and get you -3, right? So the minimax value of this game is -3. So it's pretty bad for player A. But if player B goes first, then player A can just match the number, right? So if player B goes with 1, then A is going to play 1. If player B goes with 2, A is going to play 2. And then B, knowing this, is going to play 1 because 2 is player B is trying to minimize, 2 is less than 4. Okay. So we solve this, but for these weird games that we don't really care about. But this process hopefully gives us some insight, and there's something that's worth commenting on, which is in this setting and in general, going second is no worse and often better. So in particular, this value is smaller or equal to this value. -3 is less than or equal to 2. Okay, so in more generality, max over A, min over B is less or equal to min B, max A. So going second is going to give you a higher result for player A. This sort of intuitively makes sense because if you're going second, you see what your opponent does and you can react. And since there's no state, it's not like the player A takes the card from you and now you can't take the action. You can take the same set of actions and its payoff the matrix is the same. So all you're doing is getting more information if you go second. Okay, so that's for pure strategies. Let's see what happens for mixed strategies now. Okay, so suppose player A plays a mixed strategy. So this is a little bit of a kind of a strange thing, but you're saying what this means is that player A announces their strategy. I'm going to flip a coin and with heads, if it's heads, I'm going to play 1. If it's tails, I'm going to play 2. Okay, that is what is meant by player A playing a mixed strategy. He's not flipping the coin yet, but they're announcing the strategy. Now, player B, suppose player B knows player A is going to do this. What is the best thing for player B? So now I'm going to do some very simple algebra to figure out the answer here. So just expand the definition of the game value into 4 terms, where each of the 4 terms corresponds to a different combination of actions. So each term has probability of under A, probability of under B, and then the payoff matrix entry. And then I'm going to start simplifying this. So actually I can let me actually do this on the board here since I think it'll be easier. So in this case, player A is half-half, right? Player A is uniform. And so the question is what is the best thing for player B? So player A is half over these two, okay? So which means that if I play 1, I'm just going to get the average, and that's going to be minus 1/2. If I'm playing 2, I get the average, and I'm going to play half. So what should the optimal pi b be? Yeah, you should always play 2. So it should be 0 or 1. Okay? Because half is greater than minus half. Okay. So this points out another important fact is that the second player can always play a pure strategy in this case. Right? So if the first player plays either a pure strategy or a mixed strategy, if the second player is trying to minimize this, it can always be tamed by a pure strategy. And the reason here is that suppose this were not half-half, but anything, then I can do the same math. I average, take the weighted average, I get some number, take the weighted average, get some other number, and I look at which one's bigger, and I'm going to put all my eggs in that one basket. Sure. Yeah, you're right. Okay. I got a bit confused. So player B wants to minimize. So this is the preferred choice. Okay. Okay. So no matter what player the first player does, the second player can always play a pure strategy. Okay. So hopefully we're making progress. We've made 2 observations. One is that going second is no worse. And if you go second, you can just, choose one item. You don't have to randomize. Okay, so now let's try do this more generally. So I'm going to do minimax, but where the actions are actually mixed strategies. Okay, so player A is going to go first now, and play a strategy with just P, with probability P, play 1 finger, with probability 1 minus P, play 2 fingers. Okay, so the way to think about this is you have an uncountably infinite number of possible actions that player A can take. And then at this node, player B, remember from this observation, the optimal thing is just to play a pure strategy, so there's only 2 possible values, 1 or 2. Okay? So now we just have to compute what the value of the leaves are. So if player A plays P1 minus P, and player B plays 1, then the game value is basically P times 2 plus 1 minus P times minus 3. Okay, so just to write this out here. So now I'm going to assume that this is a P, 1 minus P. So I have P, 1 minus P here. And so now this quantity is 2P minus 3, 1 minus P, which is 5P minus 3, I believe. And this is going to be minus 3P plus 4, 1 minus P. That is, what is that? That is minus 7P plus 4. Hopefully that matches what I have. Okay. Okay, so I have the game values here, and then I'm going to choose, which one I'm going to take the max over these 2. And that's going to be, that is going to be the minimax value of the game. So it's exactly what we did before, now with P instead of plugging in half and half. Okay. Sorry. You're right. I should be taking them in. So maybe we'll consult this equation now. So the minimax value of the game is I take a max over P, the continuous value, and then I take a min over these 2 values. It's a bit weird because I have this infinite number of actions here, but hopefully if you can generalize all our intuitions for minimax into this setting. Okay, so just jumping ahead here, the way you solve one of these things is this minimum is obtained when these 2 quantities are equal. Let's see if I can try to draw it. Maybe I'll draw it. I don't think I can get exactly to scale, but basically you're taking the min over 2 things. So 5P minus 3, so kind of looks like this. And so this is P, and this is, let me try to use a different color here. Looks something like this. This is definitely not the scale. But I'm taking the min, which means that I erase these two pieces. So this is like 5p minus 3, and then this is minus 7p plus 4. And if you set them to equal, you get basically this max value. Okay, so when you set them equal, if you have 5p minus 3 equals minus 7p plus 4, then you find that p equals 7/12. And then if you plug in the actual p into one of these, either one of these, then you get that the minimax value of the game is minus 1/12. Okay, so a bit of algebra, but the upshot here is that we are still making this turn-based, where player A goes first with a mixed strategy, and player B goes second with a mixed strategy, which can also be a pure strategy because they're going second. And then we compute the minimax value of the game, which is minus 1/12, where the player A is playing 7/12. So this favors player B, right? Because player B goes second. So now it's, just to be fair, let's give player A a chance to go second. So now let's let player B go first and do the same calculation. And if you do it, which I'm not going to do again, you're going to notice something remarkable that happens, which is that the min-max value of the game is exactly the same, minus 1/12. And the probability is 7/12. Okay, so you might think, okay, I rigged all these numbers, so we just kind of got lucky here. But this is actually not a coincidence. It turns out that there is a very important theorem in game theory called the minimax theorem. This comes from John von Neumann from 1928, which says that for every simultaneous two-player zero-sum game, as long as you have a finite number of actions, we have 2 actions here, so that definitely counts. Going first and going second is the same. Okay, so which, in other words, max over pi A, min over pi B is the same as min over pi B, max over pi A. And it's important here that pi A and pi B has to be over mixed strategies. As we saw in the first example, if pi A and pi B are pure strategies, this is definitely false. Right? Going second, if with a pure strategy, is going to be always favorable. Okay, so the proof of this is actually linear programming duality. It turns out this is a linear program, and there's some really nice math that shows you that this is true. And furthermore, you can compute the optimal mixed strategies very efficiently using linear programming as well. So we just solved the linear programming sort of manually for this example, but you can solve this for any number, any payoff matrix and any number of actions. But the upshot of all of this is that revealing your optimal mixed strategy doesn't hurt you. So answering the poll question from before, you can go ahead and announce to all your friends that for two-finger Mora, this is the strategy you're going to play: 7/12 on 1, 5/12 on 2, and you won't, suffer. Okay. So it's sort of bizarre that it works out, but it's math, so you can check the math, but then once you've checked it, you kind of have to trust it. Okay, I'll skip that part. Okay, so if you go back to the minimax principles, which we covered before for turn-based games, the same thing applies here. If you're at a minimax, these are minimax strategies. okay? Which means that if your opponent deviates from that strategy, it can only be good for you. And furthermore, if you deviate from your own strategy, you can only make it worse. Okay, so minimax is this really nice setting where you want to be playing minimax so that your opponent can't, there's nothing your opponent can do, and you can't do any better. And of course, the same idea of minimax being optimal against a perfect player makes sense. If you, for example, knew that your player was I'm player A, and you're always going to play 2 fingers, then of course I can do better. I can just play 2 fingers as well. So remember, expected max is the best thing if you know what your opponent's going to do. But if you don't know what your opponent's going to do, doing the minimax thing guards you against any sort of potential huge downside. So let me cover non-zero-sum games. So this is going to be just a brief overview just to get you some exposure. We're not going to have time to go through it. So the idea with non-zero-sum games is that it's not zero-sum. So the utilities of the players are arbitrary. Before we had always, so far in this class, we have assumed the utility of player A plus the utility of player B is 0. In other words, utility of A is minus utility of player B. So there are many possible settings you could be in. If you're playing competitive games, that's zero-sum. If you win, I lose. If I win, you lose. Okay? There are cooperative games where the utility of all the players are the same. There's nothing really to be said there because there it's just pure maximization. It's just search because everything is a max. And real life is somewhere in between. So here is an example. How many of you know about prisoner's dilemma? Okay, so this is more popular. So the idea here is that you have 2 players. The prosecutors asked both of them to testify against each other. Both are accused of doing something bad. If both testify, then they're sentenced to 5 years in jail, both of them. If they both refuse to testify, then they're both sentenced to 1 year in jail, which is, I guess, better than 5 years in jail. And if only one testifies, then they get out for free, and the other one gets a 10-year sentence, which really sucks. So this is going to be captured by a payoff matrix, where now I have to have a subscript P to denote the utility of a particular player. So if the utility is minus the number of years in jail, this is what the payoff matrix looks like for the prisoner's dilemma. If they both testify, -5, -5. If they both refuse, -1, -1. And then on off diagonals, if A testifies and B refuses, A gets off and B gets thrown in jail for 10 years and vice versa. Okay, so we don't have time to let you guys play this, but that's fine. So how do you solve non-zero-sum games? So we can't apply von Neumann's minimax theorem anymore because it's not zero-sum. But it turns out we can get something, and that's called a Nash equilibrium. So a Nash equilibrium is a pair of strategies, pi A star and pi star B, such that no player, A or B, has an incentive to change his or her strategy. So in other words, if pi A tries to change, that's going to only make it worse. And if pi B tries to change, that's also going to make it worse. Okay? So this is a Nash equilibrium. And in 1950, Nash proved this really beautiful theorem, the existence theorem, which says that as long as you have a finite number of players and finite number of actions, there exists at least one Nash equilibrium. So there is at least one solution. So here's some examples just to give you some intuition of what Nash equilibria look like. So we looked at two-finger Mora before, And the minimax strategy is also a Nash equilibrium because no player has an incentive to move off what they're doing. If you consider a fully collaborative version of this, where both A and B have the same reward, then there's two Nash equilibria. Either both play 1 or both play 2, right? And it's stable because if you're here, even though it's not optimal, if B tries to move off, then it's just going to make it worse for everyone. Okay, so this is a local optimum. So local optimum are also Nash equilibrium in search problems. And then finally, the Nash equilibrium for Prisoner's dilemma is both players testify. Okay, because no one has a incentive to move off. Okay, so the point here is that both refusing is not a Nash equilibrium, because if you're in this state, someone's going to, like, if I'm here, then both A and B are going to want to testify and get out for free. So this is not stable. And of course, if you're here, then that's also not stable because B is going to try to move here. Okay, so this is only stable point. And the whole point of Prisoner's dilemma is that, sometimes, unfortunately, because if you have agents that are only after their own selfish interest, you can get into situations which are suboptimal. Clearly, this is better for both of them, but it is not a Nash equilibrium. Okay, so just to contrast, simultaneous zero-sum games. Here we have a von Neumann minimax theorem. We can produce a single game value. And in non-zero-sum games, we have Nash's existence theorem, and that can lead to multiple Nash equilibria and multiple game values. So the way to think about Nash equilibria is that they're just stable. They're locally stable, so no one can change, no individual agent can change something. It's not really about optimality in the same way that we've been pursuing in the rest of this class. And it sort of makes sense because everyone has different utilities. What is optimal with multi-objective even mean? And fortunately, they do exist for non-zero-sum games. Okay, to summarize, we looked at simultaneous games. Two players move at the same time. In general, second player has an advantage and play a pure strategy, but the minimax theorem says if you allow for mixed strategies, then second player doesn't actually have an advantage. Both players can be optimal. And then we look at Nash equilibria exists for non-zero-sum games, but it's not unique. And in general, there's a huge literature in game theory and economics. So if you like this, second half of this lecture, you should go take a game theory course and learn more. Okay, so that concludes the game unit and all our work on state space models. I'm going to start a brand new unit on Bayesian networks. Okay, see you next time.